In this video, we consider the bootstrap, which is a non-parametric method for estimating standard errors and hence computing confidence intervals using simulation. We have a quantity here, Tn, which could be either a statistic or a parameter, or a vector of statistics or parameters, and we want to estimate that from a data sample x1 up to xn. The point estimate is then denoted by hat Tn, and it will be some function of the data. The standard error is simply the standard deviation of the point estimate, which I remind you is a random variable because it's a function of random variables. Now we will assume that the data x1 up to xn are independent and identically distributed draws from some unknown distribution f. In that case, the empirical cumulative distribution function is simply given as follows. Hat fnx is the proportion of the data points which lie below x. And that's an approximation of the cumulative distribution function f. In other words, the observed data has distribution hat fn. We let v, t and f denote the variance of tn, given that the true distribution is f. The bootstrap works as follows. You approximate v, t and f using its empirical distribution function. In other words, this is a plug-in estimator. And then we compute the variance Vt and Fn by simulation by drawing from this empirical distribution. Let's illustrate what we mean when we say that we draw from the empirical distribution function. Here we have an original distribution function which is standard normal, and we take a small sample of 20 variates from that distribution. We then plot the ECDF, and that will be an approximation of the true distribution function f. It won't be a good one because we keep n quite small in this case, just so that we can clearly see what's going on. So let's do that to begin with. And this is then the approximation. Of course, the true CDF is a nice smooth function. It's S-shaped. Now we're going to sample 20 data points from the data X, and we're going to sample with replacement. That means that some of the data points in X might be sampled more than once, and others might not be sampled at all. In MATLAB, the command for this is rand sample xn true, true meaning replace equals true. We'll let G be the ECDF of this new sample Y. All the points in Y are points in X. I'm going to plot the original ECDF that we have shown here in blue, and we're also going to plot the ECDF of Y. Now, as you can see, every single time Y has a jump, X also has a jump, although X has jumps at points where Y does not. For example, if we consider this point here, this is a point in X but not in Y. It's in X because X has a jump here, but Y does not have a jump here. On the other hand, this value over here, X has a jump, it's a small jump, but Y has a big jump because this point occurs in Y 3 times. Now, if I increase the number of samples from the same distribution X, in other words, suppose I choose, say, 10,000 points from X. X only has 20 points, so there will be lots of duplication. Then the ECDF of Y will be almost exactly equal to the ECDF of X. We can repeat this a few times. In other words, by drawing with replacement from the sample X, we obtain an approximation of the ECDF of X, and the ECDF of X is an approximation of the true distribution f. Now recall that by definition, the empirical CDF hat fn has a mass of 1 over n at each of the data points x1 up to xn. In other words, drawing a point from the distribution hat fn is equivalent to drawing a random point from the original dataset x1 up to xn, where each point has the same probability 1 over n. That's what we just illustrated using computer code. Now we're interested in the variance of the point estimator Tn. And we do this via simulations as follows. Let B be a large number, 500, 1000, 10,000, and draw B many samples of length n from head Fn. In other words, construct B many samples by drawing from the data that you have, x1 up to xn, and sample with replacement. So in MATLAB, as already mentioned, you can use rand sample xn true, and that will draw n points, capital N points, from the data vector x with replacement. But you want to do that B many times so that you have B many samples of length little n. So now you have B many new samples, and you compute the point estimate of Tn for each of these new samples. So you now have B many new point estimates obtained from the same dataset X, but by sampling with replacement. The bootstrap variance is then estimated as follows. We want to know the true variance of the estimator. We approximate it by replacing the true CDF with the empirical CDF. And then the variance is approximately equal to, and then the variance is approximately given by this expression over here, where T bar n is simply the mean of all the new point estimates that you have. And the standard error is estimated as the square root of this quantity here. Observe that there are two approximations here. Firstly, we approximate the true variance by replacing the true CDF with empirical CDF. And then secondly, we approximate this variance using the empirical CDF using simulation. We can make the second approximation as accurate as we like by increasing the number of bootstrap samples, capital B. But the first approximation really depends on how good the dataset is. In other words, how well it represents the true distribution, capital F. Let's now consider an example. This is number 9 on the exercise sheet. Consider again the data in bond default number.csv, which contains the quarterly number of defaults in a large bond portfolio over a period of 20 years. Read the data into a matrix R. Let X be the second column of R. So X contains the number of quarterly defaults that we see for the 80 quarters that make up the 20 years. In an earlier problem, we hypothesized that this distribution was Poisson, and we obtained a point estimate of the mean or the rate parameter as lambda hat equal to 4.937. We'll try to use the bootstrap now to estimate the standard error, in other words the standard deviation of this estimate. So let capital N be the length of X, and let B be equal to 1000, and that's going to be the number of bootstrap simulations. We're going to draw B many random samples from X with replacement, each of length n, and we'll create an n times B matrix X boot of these. So let's have a look. Let's read the data in and put it into the vector X. So our 80 element data vector says that in the first quarter there were 4 defaults, in the second quarter there were 9 defaults, in the third quarter there were 4 defaults, etc. And there are 80 of these. So now we obtain our point estimate as the mean of X, as we saw in an earlier problem. And we let capital B be equal to 1000, and we form the matrix X boot, which will be a capital N by capital B matrix, in other words an 80 by 1000 matrix. And each column consists of 80 draws from the data vector X that we saw before. So you can think of each of these 1000 columns as a possible data set that you might have seen instead of the one that you actually did see. And for each of these 1000 many data sets, we can form an estimate, which in this case is simply the mean, because the mean is equal to the parameter lambda. So we obtain an estimate of lambda for each of these columns simply by taking the mean of each of these columns. and it will be 1000 possible point estimates that we might have seen instead of the one that we actually did see. I remind you, the one that we did see was 4.937, but these are all possible values that we might have seen instead of the one that we did see. And so in essence, we have 1000 mini draws from the random variable hat lambda n, where little n is 80. And we can take the standard error simply as the standard deviation of this. And so this is the way in which we obtain a bootstrap standard error. Now in this case, we're obtaining the parameter lambda as the mean, and for the standard error of means we never need to use the bootstrap, because in general, if x has variance sigma squared, then the mean x bar has variance sigma squared over n. And so the standard error of the mean is approximated by the standard deviation of the x's divided by the square root of n. So we have our bootstrap estimate of the standard error. We can also take the standard deviation of the data set and divide it through by the square root of n, where n is 80 in this case, and we can see two values that are pretty close. Now remember, we are obtaining the bootstrap standard error via simulation. In other words, there is randomness involved, and if you do a different simulation, you will get a different set x boot, as you can see, and therefore you will get a different lambda boot, and therefore a different estimate of the standard error. The one we obtained this time is a little closer to the true value. You can also obtain a histogram of these point estimates and get some idea of the distribution. This histogram gives an estimate of the distribution of the estimator lambda hat. If you increase the number of bootstrap simulations, the values will not change much. You might get a slightly better histogram because you have more information about the distribution of lambda hat. We now consider two ways in which we can form confidence intervals using the bootstrap. The first is using a normal approximation. We suppose that the statistic Tn is approximately normally distributed. And it is the case that many estimators are asymptotically normal. In other words, they become more and more normally distributed as the sample size increases. Let alpha be greater than 0 and define z alpha to be the alpha quantile of the standard normal distribution. In other words, z alpha is equal to the inverse CDF, or the quantile function, of the normal distribution evaluated at alpha. And then a confidence interval can be obtained in the usual way. In other words, taking the quantile and multiplying it by the standard deviation, which gives a confidence interval symmetric around the point estimate Tn. The second method is via so-called pivotal intervals. Let theta equal Tf be the true or population value of a particular statistic. In other words, here f is the true distribution function and t is the particular statistics, which we will also call theta over here. So theta might be the mean, the median, the skewness, the kurtosis, etc. Let theta hat n be equal to t hat of fn, where hat of fn is the empirical distribution function that we obtain from the data, and that is its estimator, and in this case would, for example, be the sample mean, the sample median, the sample skewness, or the sample kurtosis. Now define a pivot random variable Rn as follows. Rn is theta hat n minus theta. Now observe that we actually do not yet know theta. Theta is what we're trying to estimate. Let HR be the CDF of Rn. In other words, h of r is equal to the probability that Rn is less than or equal to little r. Let h inverse denote the quantile function of h. Define a to be equal to theta hat n minus that quantile function evaluated 1 minus alpha over 2, and b be equal to theta hat n minus that quantile function evaluated at alpha over 2. And consider now the probability that theta lies between A and B. By rearranging this expression over here, we see that we get this expression here. This random variable in the middle over here is just Rn. And so what we have is the probability that Rn is less than or equal to theta hat n minus A, minus the probability that Rn is less than or equal to theta hat n minus B. In other words, this expression over here. But by definition of A, we see that theta hat n minus A is simply equal to H inverse evaluated at 1 minus alpha over 2. And so we get H of H inverse evaluated at 1 minus alpha over 2, which is just 1 minus alpha over 2. Similarly, if we look at this expression here, we get H of H inverse of alpha over 2 using the definition of B, which is alpha over 2, and so we get 1 minus alpha. And hence the interval from A to B is 100 times 1 minus alpha % confidence interval for theta. However, we still do not yet know who A and B are, because we cannot compute H, and we cannot compute H because we do not know theta. Now, though we don't know H, we can try to estimate it using the bootstrap. Let hat theta star n1 up to hat theta star nb be b many bootstrap replications of hat theta n, and define r star nb to be equal to hat theta star nb minus hat theta n. So hat theta star nb is a new estimate of theta, and hat theta n is the original estimate that we had from the data. Hat theta star nb is obtained by resampling from the data, and we can regard r star nb as a draw from theta hat n minus theta, where the role of theta hat n is played by this new estimate, hat theta star nb, and the role of theta is played by the estimate that we had, namely hat theta n. Then an estimate of the empirical distribution function hr is then given as follows. Hat hr is simply the proportion of the r stars that lie below little r. So each of the random variables r star and b can be regarded as a draw from theta hat n minus theta, and we can therefore consider the beta quantile from that sample. In other words, r star beta is the quantile function associated with h hat evaluated at beta. Similarly, we can let theta star beta be the beta quantile of these new estimates that we have obtained. Hat theta star n1 up to hat theta star n capital B. Now, because of this relationship over here, it's clear that the beta quantile of r star is equal to the beta quantile of theta star minus theta hat n. In other words, r star beta is equal to theta star beta minus hat theta n. Now, let a hat be equal to hat theta n minus the quantile h hat inverse evaluated 1 minus alpha over 2, and define b hat similarly. Then a hat and b hat are an approximate 101 minus alpha % confidence interval for theta. So a hat is an approximation of a, b hat is an approximation of b, and a hat b hat is an approximation of the confidence interval ab. Now, by definition, a hat is theta n hat minus the quantile evaluated 1 minus alpha over 2, and by this relationship here, that simplifies to this. Similarly, beta hat is theta n hat minus r star at alpha over 2, which simplifies to this. And so a bootstrap 101 minus alpha % confidence interval for theta is simply given by this expression over here. Remember that hat theta n is the original estimate that we have, and theta star 1 minus alpha over 2 is the 1 minus alpha over 2 quantile of the new bootstrap estimates that we obtained. So let's consider an example. Suppose that a dataset consists of independent draws from the Poisson distribution with an unknown parameter lambda, and it's this parameter lambda that we want to estimate. Using the fact that the mean of the Poisson lambda distribution is lambda, a method of moments estimate of lambda is computed as follows. Lambda hat is 3.97. Never mind how the method of moments works right now, just know that it is a method for obtaining certain parameter estimates. The bootstrap with b is equal to 100 simulations is used to estimate a 90% confidence interval for lambda. And these estimates are ordered from smallest to largest, in other words from lambda 1, the smallest, to lambda 100, the largest. Some of these are shown in this table over here. So the smallest is 3.71 and the largest is 4.17. We want to compute a 90% pivotal bootstrap confidence interval for lambda. Now let's have a look at the solution. Lambda hat, as we're told, is 3.97. We want a 90% confidence interval, so alpha is equal to 0.1. This is the 0.95 quantile of the bootstrap estimates, and since there are only 100 of them, it's the 95th one. In other words, it's equal to 4.06. Similarly, the 0.05 quantile, or the 5th percentile, is the 5th one, which is 3.82. Then the bootstrap 90% confidence interval is going to be given by this. Here we have the original estimate of 3.97. This is 4.06. And this is 3.82. And when we work it out, we see that a lower bound for the confidence interval is 3.88 and an upper bound is 4.12. One more example. Consider the data Microsoft Daily Returns 2005 to 2015.csv. Use the bootstrap to determine a point estimate for the kurtosis as well as an estimate of the standard error. Also compare normal and pivotal confidence intervals for the kurtosis of the Microsoft Returns data. So let's read the data. And as you can see, we have 2,517 daily returns. And we obtain a point estimate by taking the kurtosis of these returns, and the kurtosis here is 10.37. Then we set the number of bootstrap simulations to 500, and we create a matrix of bootstrap simulations. So there are 500 columns. Each column has the same length as the data set. And you can think of each of these data sets as a possible set of returns that you might have seen instead of the one that you actually did see. We can obtain the kurtosis of each of these columns. That will give us 500 different estimates of the kurtosis, and as you can see, they can vary quite widely. The standard error is simply the standard deviation of these estimates. So we have a point estimate, as we already worked out, of 10.375 and then a standard error of 2.479. Now, if we want to work out a 95% confidence interval, then we set alpha is equal to 0.05 and we work out the lower bound, which is twice the original estimate minus the 95th percentile of the bootstrap estimates. And similarly, the upper bound of the confidence interval is given by twice the original estimate minus the 5th percent quantile of the bootstrap estimates. And that gives us pivotal confidence intervals of 5.68 to 14.73, which is quite wide. We can also obtain the normal intervals using the normal distribution, assuming that the estimator is asymptotically normal, and this gives us confidence intervals that look like this.